Hello, and welcome to another video with Takoa Lawson. We're going to be working through another lesson from the Introduction to AP Physics. We're going to start by looking at scientific notation, which is a really important way of expressing very large or very small numbers. When we're looking at scientific notation, it's really about understanding the different parts. There's a couple of important parts. One is that there is some times 10 to an exponent, and the times 10 never changes. You'll always see some digit or number times 10 to some exponent. So since the times 10 never changes, we want to make sure we're clear about that fact for all scientific notation. What can change is what the beginning part of the scientific notation is, which is known as the digit, sometimes referred to as the coefficient, the significand, or the mantissa. But that digit right there has a very important rule. It has to be greater than or equal to 1 and less than 10. That means it can be 1.0, 1.000, any number of zeros after the decimal place, but it cannot be 10 decimal place. It can be 9.9 bar, which means it can go up to almost 10, but it cannot equal 10. So the very important rule for the digits must be greater than or equal to 1 and less than 10. Cannot be equal to 10, and that'll be important when we start talking about significant figures related to those values. The second part of the scientific notation is the exponent. That's the factor that goes on to the 10. That can be any number between negative infinity and positive infinity. But for scientific notation to be in its proper form, it can only be integers. Now, exponents can have decimal places, but in scientific notation, the exponent on the scientific notation can only be an integer. It can only be an integer between negative infinity and positive infinity, so any number, but it has to be a whole number, no decimal points on those values. We're going to look at a couple of examples of how to convert between scientific notation and standard notation. This should be review and hopefully something you're already comfortable with. First, let's look at the standard notation values. We're going to start with 456,353. Now this number is clearly much bigger than 1, but the digit, which is the part we have to figure out first, can't be greater than 10 and it can't be less than 1. So when we're moving the decimal place, when we're trying to figure out where should the decimal place go along this number, there's only one place that's possible. It always has to be to the right of the first non-zero number. Now, if it's to the right of the first non-zero number, that means there's one digit before the decimal place. That one digit has to be a 1, 2, 3, 4, 5, 6, 7, 8, or 9 because it's not 0. And in that case, that number will always be between 1 and 10. It could be equal to 1 if it's 1.0, but it can't be equal to 10 because that would be two numbers to the left of the decimal place. So now that I know where the decimal place goes, I look at the rest of the values and I add them in after the decimal place. So it's 4.56353. Now that's the digit part. Then I have to multiply it by 10 to some power. That part never changes. How do I know what that exponent is? Well, that exponent is what gets me back to my original number. If my original number is greater than 10, it has to be a positive exponent. If my original number is less than 1, it'll have to be a negative exponent. And if my original number is close to 1 or between 1 and 10, then I actually don't want to move the decimal place because that's already going to give me my digit, which means my exponent will actually be 0. In very rare cases, the exponent will be 0 to get a number. The thing is, scientific notation is intended for very large or very small numbers. It wouldn't make a lot of sense to use scientific notation for numbers that aren't very big or aren't very small. However, you want to be able to do it for any number, so we'll also practice those. So now I can see, to get the decimal place back, 1, 2, 3, to move it back 1, 2, 3, 4, 5 places, I would need an exponent of 5. And that's how this number written in scientific notation. I'm going to move a little faster now that we've done that. Decimal place to the right of the first non-zero number, which is a 3. That gives me 3.85 times 10 to some power. That number is greater than 10, so it's going to be a positive exponent. I have to move it 2 times, so it's an exponent of 2. decimal point goes between 6 and 2. That's to the right of the first non-zero number. That's 6.2. That number is greater than 10. I have to move the decimal place one place. So that's times 10 to the first power. In this case, I'd have to move the decimal place 1, 2, 3 places to the right to get to the right of the first non-zero number, in this case, which is 8. I write 8.32 times 10, and this time it's less than 1, so it's a negative exponent, or I'd have to move the exponent back 3 places to get the original number. Now those numbers are all written in scientific notation. Very important part about scientific notation that's not just about writing large or small numbers, because all of the numbers are significant digits. We don't use the exponents. The exponents aren't considered part of the significant digits, but all the numbers in the digits are significant figures because it can't be less than 1, so there would be no 0 point anything, so there's no leading 0. It has to have a decimal place because it's got to be greater than 1 and less than 10 to have any numbers after the decimal point, which would be any zero. So all zeros that would come after any number are trailing with the decimal point, so they're always significant. And then sandwich zeros are always significant. So all the numbers that you would see written in scientific notation always have to have the correct significant figures. So that first number has 6 significant figures. The second number has 3 significant figures. The third number has 2 significant figures. And the fourth number has 3 significant figures, which are all easily seen from the values in the digits part of scientific notation. Now let's practice going in the opposite direction. Here we can see this is 2.75 times 10 to the negative fourth. It's a negative exponent, so you move the decimal place to the left 4 times. Now if I move the decimal place to the left 4 times, I'm going to end up getting 3 zeros between the decimal point and the 275. I can see that the number written in standard form is 0.000275. I can also see that number again has 3 significant figures. There's a few numbers that can only be written in scientific notation to show the correct number of significant figures. We'll talk about that in 1 second too. Here I see 9.226 times 10 to the 0. That's that strange instance where we have 10 to the 0. Now, sometimes students get confused and don't remember that the 0 exponent is not equal to 0. 10 to the 0 is not 0. 10 to the 0 is 1. So all we're doing is saying multiply that by 1. Which is why we see it's a little bit strange to write something times 10 to the 0, because it's just extra work. The number is really just the digit, 9.226. And again, we see that there's 4 significant figures in the digit, there's 4 significant figures in the value. 5.7 times 10 to the 6th. We move the decimal place to the right 6 times, which means we have 5 zeros between the decimal point and the 7, which means this is now 5,700,000. And we can again see that those trailing zeros are not significant. We wouldn't draw the decimal point there because this was just 5.7. It would have to be 5.700,000 times 10 to the 6th for all those zeros to be significant. When we think about that, it's also important. What if we wanted to write 5,700,000 to 4 significant figures? Well, to have 4 significant figures, I'd have to have 2 of those trailing zeros count, but then 3 of them not count. These 3 would have to be placeholders, these 2 would have to be significant. If I put a decimal point, they all count. If I don't put a decimal point, none of them count. The only way we can show 5,700,000 to 4 significant figures is by writing it in scientific notation. And you can see the real power. Sometimes the only way getting a specific number of significant figures is in scientific notation. If we were going to do that for this value, it would be 5.700 times 10 to the 6th. And now, since those 2 zeros are after the decimal place, and we see the decimal place, those 2 trailing zeros are significant. So now we have 5,700,000 to 4 significant figures. And the last one, we have to move the decimal place to the right 11 times. 4 of them get us past the 3, which means there's going to be another 7. So we have 1, 0, 9, 4, 3, 1, 2, 3, 4, 5, 6, 7. And that's how we're able to see that final number in standard form. Now we get to an important part about significant figures. Before you can do this, you have to make sure you're comfortable with identifying significant figures. Non-zeros are not a big deal. Zeros are a little annoying, but hopefully you've memorized the rules. Once you've memorized the rules to determine the number of significant figures in a value, you can start to use those measurements in calculations. Now there's basically three types of calculations you'll be doing with measurements or significant figures. You'll either be multiplying and dividing them, adding and subtracting them, or you could be using them in exponents or logarithms. In this class, it's not very common you'll be working with logarithms, but you want to be familiar with them, and you definitely should be able to do them in case you're working in a chemistry class. But on occasion, you might find yourself using them in this class, or if you go into a higher level, you could definitely be using them in that class. And although most of the time we'll have exponents that are in scientific notation, so they'll never have any decimal places, so they'll be nice and easy and they won't affect significant figures. If we're using a measurement as an exponent, then the significant figures of that exponent. First, let's look at how we would use significant figure measurements or significant figures, or when we're multiplying or dividing. Then we have to follow a very specific set of rules. Students usually find this one to be the easier set of rules to memorize for some reason. Some of you, I'm sure, will find the addition subtraction easier, but oftentimes counting the number of significant figures seems to be an easier strategy, or something that sticks a little bit easier in some minds. So the strategy is pretty straightforward. You count the number of significant figures in your values, you perform the calculation, and then you round your answer to the number of significant figures that is equal to the smallest number that you used. It might sound a little wordy, but essentially it's just counting how many significant figures there are in a value, and then determining which value had the least number of significant figures, because that's how many your answer should also have. So it's all about focusing on the number of significant figures in the different values. Let's look at a couple of examples. First, we're going to multiply the two values, 2.10 and 0.5896. Again, the first strategy is to remember the rule. The rule when you're multiplying and dividing is the number of significant figures. 2.10, the 2 and the 1, non-zeros, are always significant. The 0 is a trailing 0, which can be significant, but only if I see a decimal place. There's a decimal place visible here, so since we can see the decimal place, this is a significant figure, which means that this value has 3 significant figures. Now we look at 0.5896. The 0 is a leading 0, which is never significant, so we see the 5.896, which is 4 significant figures. Now, 3 is less than 4, so our answer has to have 3 significant figures. If they both had 3, then it would be easy. If they both had 4, then it would be easy. It's only when they're different numbers we have to figure out which one is the smaller number of significant figure. The calculated answer that we get is 1.23816. Now, that answer has 6 significant figures in it, which is not equal to 3 nor 4. So what we have to do is figure out where's the third significant figure. And the third significant figure is the 3. Now that I know where I'm rounding, I apply the normal rounding rules. 5 or greater, we round up. 4 or less, we round down. 8 is greater than 5, which means we round up. So this, to the correct number of significant figures, is 1.24. The same exact rule applies for division. The only difference is instead of multiplying, we divide. So when we look at 16.15, we see that there are 4 significant figures. 2.7, we see 2 significant figures. 2 is less than 4, so our answer needs to be rounded to the second significant figure. We get a complete calculation of now that has 5 significant figures in it. Our answer can only have 2 significant figures, so we go to the second significant figure, which is greater than 5, we round up. So to the correct number of significant figures. If you think back to the last lesson when we were looking at percent uncertainty, It was rounding to one significant figure, and it was based on the fact that our uncertainty had one significant figure in it. Since we were dividing and multiplying, we applied that rule. The 100 was a count. There's exactly 100 parts in a percent. So a count has infinite significance. That should make some sense with the exponents in scientific notation too. The digit has significant figures, but the exponent is a count. It's how many places you have to move the decimal place to the left or to the right. And since a count has infinite significant figures, the exponents of scientific notation don't affect the significant figures of the value. When we're adding and subtracting, we have to apply a different set of rules. We have to memorize the rules for addition and subtraction and recognize that they're not the same as multiplication and division. In multiplication and division, we look at the number of significant figures. In addition and subtraction, we're looking at the place value of the smallest significant figure. The place value of the smallest significant figure is going to be the significant figure furthest to the right in that number. That's going to be the smallest place value in any number, and so we're looking for the significant figure for that value that's furthest to the right. Again, it sounds wordy when you just see it. When you see some examples, hopefully it'll make some sense. We're going to add 1.586 and 2.31. So again, we're going to look at the place value of the smallest significant figure. The smallest significant figure, or the significant figure furthest to the right, is in the thousandths place. That means that this is the thousandths. The one furthest to the right in 2.31 is the 1, and that's in the hundredths place. We're not looking at the number of significant figures, we're looking at the place value, and thousandths are smaller than hundredths. So we go to the largest, smallest significant figure. Right, the largest, smallest. What am I talking about? What we're saying is that the uncertainty in these numbers, whatever one has the biggest uncertainty, that wipes out any smaller uncertainties in the other ones. This value on the left, our certainty goes out to the thousandths place, but the number on the right, the uncertainty is in the hundredths place. Plus or minus a hundredth is going to wipe out anything in the thousandths place from the other one. So our answer has to be rounded to the largest, least known value. Hundredths is the largest, least known value in this case. So first we sum up the two numbers. We get the answer. Then we have to figure out which place value we're rounding to. We're rounding to the hundredths. At the hundredths is a 9. After the 9 is a 6, so we round up. Now if you round 9 up, you get 10. That turns into a 0, which means it carries over. So we're going to round that to a 0, but that means it carries over and bumps the one to the left of it up 1. And that's why this will be 3.9, but we have to include the 0 to have that significant figure place in the hundredths. So this would be 3.90 as the answer computed to the correct number of significant figures. When we're doing subtraction, we apply the same rule. Here we have thousandths place. Here we have the 10,000ths place. Thousandths is larger than 10,000ths, so that's going to be where we round to. First we compute the answer. 0.6431. That's the complete answer, and then we see that we go to the thousandths, tenths, hundredths, thousandths. So we round it to 3. After the 3 is a 1, 1's less than 5, so we round down. So this will be 0.643. Not about the number of significant figures, it's about the place value of the significant figures. When you're using exponents or logarithms, it's a slightly strange rule. So when we have an exponent that uses a measured value, we actually look at the number of decimal places in the exponent. However many number of decimal places are in the exponent will tell us how many significant figures our answer should we use in the logarithm determines how many significant figures there will be in the computed answer. Here we see 10 to 9.50. Students might ask, when would you have a measured exponent? Again, not very common in physics, but in chemistry, let's say you're measuring the pH. If you were measuring the pH as 9.50, then that would determine the number of significant figures in your answer. So we see, when we look at that exponent 9.50, we see that that means our computed answer should have 3.16228 times 10 to the 9th. Now that has way more significant figures. So this times 10 to the 9th. We're doing computation with a logarithm. Here we're going to do log of 4.50 times 10 to the 5th. Computed answer is 5.65321.